We're going to start over here on this board.
I'm paying attention to this.
And I'm going to leave this up here probably through tomorrow. Maybe even longer, it just depends. But this is just a summary of all the information that we have right as all of these things are being published. Okay? So we start with, we have the Rutherford model of the atom. And the Rutherford model of the atom says that the nucleus is small, it's dense, it's positive, and it's in the center of the atom. The electrons are outside of the nucleus. We're not real sure anything what's going on with them. We don't know what structure they have, but we know they're not in the nucleus, and we know that they're there. But Rutherford's atom could not explain the chemical and physical properties that we see for the different elements. It could also not explain why elements gave off light when they were heated. So we have Rutherford's model, but we don't know anything about where the electrons are exactly. We don't know how that relates to the chemical and physical properties of the elements or why they give off light when they're heated. Okay, so that's what we have, and some of the things we don't know. Because they give off light when they're heated, that means that we need to talk a little bit about light. So just some generic information about light. Light exists as a wave. We can describe that wave with wavelength and frequency. There's an inverse relationship between wavelength and frequency. That means that if the wavelength is really tiny, the frequency is very high. So one is low, the other is high, they move in opposite directions. The other alternative, sort of the other end of that spectrum, is that we have a really high wavelength and then we have a very low frequency. Now frequency is measured by how many waves pass a sensor per second. So if this is my sensor, a wave that's really bunched up is going to pass that sensor. There's going to be a lot of them that pass because they're really tightly bound up. But if we stretch it out, in 1 second, not as many waves are going to be able to pass, which means the frequency is going to be lower. So this relationship is important. We know that we can go back and forth between wavelength and frequency using the speed of light in a vacuum. This is sort of that conversion between wavelength and frequency. I also have listed here the colors of the rainbow going up, because red has a very low frequency in the visible spectrum, and as we move our way towards violet, the frequency increases. So that's just some generic information about waves, about light waves. So now that we have this idea that we're giving off light and we have these waves, Max Planck, who is working with different substances, and he's heating them up, and he's studying how they cool down. He's also studying the kind of light that they give off. So when objects are heated, they give off specific frequencies of light. Max Planck, his big contribution is this, that matter can gain and lose energy in small, specific amounts, and he called those small, specific amounts quanta. Quantum is the singular version of that, and the definition of a quantum is the minimum energy gained or lost by an atom. So atoms have to lose or gain energy in small amounts, and those small amounts are set. There's not any variation in it. They are this amount, but not a little bit more or a little bit less. It has to be a very specific amount. Now, what Max Planck's work did was it showed us a relationship between the light frequency and the energy that's carried by that light. We can use his equation, E equals h nu, to calculate the energy that's carried by a specific frequency of light. We can also calculate the energy that is provided by a light that has a specific frequency. I think I said the same thing twice. We can also say we need this amount of energy. We can calculate the specific frequency of light that will deliver that amount of energy. Okay, so that's Max Planck's work. For a while now, the photoelectric effect has been out, and Albert Einstein, who is working in a patent office at the time, is staying current with the physics research that's going on. And he came across Max Planck's work, and he came across the photoelectric effect, and he was able to explain what was happening. Based on the publication of Max Planck's work, he was able to say, well, clearly, light is behaving as a particle. So the photoelectric effect is you have a light frequency come in, it hits the plate. If it gives it the electron enough energy, the electron will jump from the plate to the post. If the frequency is not the right amount, then nothing happens. But if the frequency is a minimum amount, and it can't just be, like our minimum is 100 hertz, it can't be anything above 100 hertz, it's usually a multiple of that. So 100, 400, 700, 1200, it's gotta be a multiple of that minimum frequency. If that energy comes in here, that wave comes in here and hits the metal plate, it generates an electron that can jump from the plate and it hits the post. Einstein said that only happens because the frequency is being carried by a particle of light instead of a wave. So he called that particle of light a photon, and he also said that a photon carries a quantum of energy. Now, quantum of energy is not the same for every substance. It can be calculated, but it carries just the amount of energy that the electron needs in order to jump from the plate to the post. Photons with specific frequency have enough energy to eject an electron from a metal surface. And by using Max Planck's equation, he was able to calculate the energy needed to eject the electron, based on the frequency of light that caused that to happen. So here we're starting to see a connection. Okay? That brings us to atomic emission spectra, and this is what you guys did with those lights in the carousel. Atomic emission spectra are unique for every element. They're like a fingerprint. What we observed with that carousel was visible light, but there are bands of light in the infrared and the ultraviolet as well, and in some cases in some of the other areas of the electromagnetic spectrum. Electricity is passed through a sample which causes it to glow, and it emits certain frequencies of light that can be seen using a spectroscope. That's what we did with the spectroscope in the carousel of light. Now, I want to make the connection. I want to make the connection for you between what we know is happening here and what he did here. Max Planck heated things and looked at the light that was given off. And generally when you pass electricity through something, you heat it. And it also gives off light. So these bands are related to photons that are absorbed or released by the atoms of the sample. I want to make the connection here. Because, from the bands of light back here to Max Planck talking about how they can only gain or lose very specific amounts of energy. Here we're looking at this gain or loss of energy by these atoms. And we can calculate the frequency needed to absorb or release a certain amount of energy using Max Planck's equation. So now, that was a lot of information, very fast. What questions do you have for me? Ross?
Is there any way that you can take a picture of that and post it in classroom, or would you like us to take our own?
Actually, I'm going to leave it up there.
Okay.
There is value in you writing it.
Okay. No, yeah, I was gonna write it, but I just.
Yeah. So when I have to erase it, I will take a picture of it. But for right now, I'm just going to leave it up there.
Okay.
Any other questions? Because I feel like some of you have like deer in headlights look. And that's perfectly reasonable at this point. Here, you can't shut down on me. Can't shut down on me. So that's a lot of information. It's still very abstract, and it's not, I haven't pulled it together for you yet. But it's an important aspect of this discussion. Yes, Melena.
So can you at least tell us what we need to know, what we need to pick up of what you're telling us? Like, is that everything up there what we need to understand? Or is that just background facts to help us understand for the future?
Yes and yes. Okay, so here's the thing. When we get into some of these advanced classes, and especially in my classes, I I mean, you know how I am. The goal is for you to demonstrate your understanding. So you might need that information to demonstrate your understanding of something else. Now, I will be asking you to explain some of those aspects on a test. But again, Jaden, you have to trust me. You have to trust that I have done this long enough and I know kids and I know what I'm doing, okay? So, it's still very abstract and it's like, it feels very independent because we haven't pulled it together yet. And I know, and I've shared with you many times, that our understanding is enhanced when we can connect it. So, let's go ahead and do that today. Okay? Jaden, did you get your application filled out?
No.
He's trying to figure out.
I can't find the CCP.
Okay. And Brayden?
Oh, wait, I found it.
Okay. Okay. So we're actually gonna do these notes today.
Yeah, like the light and the atoms just not connecting.
Wait for it. Because some of it is gonna connect today. All right, so quantum theory and the atom.
I think I found it.
So I want to introduce you to a very intelligent young man by the name of Niels Bohr. He's a Danishman. He is, he's a physicist. He's a physicist. And he was working in Ernest Rutherford's lab when the nucleus was discovered and when they discovered the proton as well. So Niels Bohr has first-hand knowledge of all of the discussions and all of the data that they collected in doing that gold foil experiment and then further experiments to determine where the proton, or that the proton was in the nucleus. So, incredibly intelligent man. He rubbed elbows with Albert Einstein. There's a huge number of very intelligent people that are contributing very important understandings during this time. And this is in 1913, so just over 100 years ago is when Niels Bohr proposed his model of the atom. Because we knew that Rutherford's model was not going to cut it. It didn't explain really anything that we needed as chemists. We need to know what causes chemical and physical properties, and Rutherford's model just wasn't cutting it. So Niels Bohr proposed a new model, and I have it pictured right next to the words here. The really impressive thing about this is that he was able to make a connection between the model he proposed and the atomic emission spectrum for hydrogen. Okay, now hydrogen has, on its atomic emission spectrum, hydrogen has a red band, a blue band, and 2 purple bands. Okay? And if you're curious, you can come up here and see it on this poster. It's like the second one from the bottom of the emission spectrum. So let's talk about his atom. And we use these all the time, so those of you that are seniors have seen this with me in the past. But we're going to take it a couple steps further. So this is what we refer to as the Bohr model for hydrogen. Hydrogen has 1 proton in its nucleus. You can see it here, which is at the center of the atom, positively charged. And it has 1 electron in the atom. I apologize. I feel like that's a doctor's office. It'll be fine. Okay. So it's got 1 electron, and in Niels Bohr's model, that's hard to say, Niels Bohr's model, in Bohr's model of a hydrogen atom, we have these, we're going to call them energy levels. Okay, we have these energy levels. And the energy levels are labeled N equals, in this case, the first one is labeled N equals 1, and then N equals 2, and it would just go out from there. In every atom, there are an infinite number of energy levels. There are two of them drawn here. The one closest to the nucleus has the lowest amount of energy. And electrons, just like everything else in the universe, likes to exist at its lowest possible energy. So the electron is in this first energy level, N equals 1. Well, we know, because of the photoelectric effect, that if we have energy, as in the form of a photon, come in here and hit that electron, if it has the right amount of energy, it can cause the electron to absorb that energy. So I'm just gonna show you that. Let's say that we have a photon come in here and it's just the right amount of energy. And it hits that electron. So when that photon, which is pure energy, comes in and it hits that electron, if it is the right amount of energy, if it's the right frequency, that electron will absorb that whole photon. It just absorbs it, like gobbles it up. But remember I said that this electron likes to be in its lowest energy possible. It just absorbed a bunch of energy, so it can't exist in energy level 1 anymore. So what happens is, this electron, now that has too much energy to be in energy level 1, what do electrons like to do?
Jump.
They jump. So this electron might now have enough energy to jump to that second energy level.
So that's how they do it, is because they can't stay in that energy level.
Yes. Because there are restrictions on how much energy the particles can have in those energy levels. So that electron jumps from the first energy level to the second energy level. But if there's another photon that comes through there, and it's not the right frequency, the electron is snobby. It's going to say, I don't even see you, and it just goes about its business. It's got to be the right frequency in order for that to happen. Okay? Now, I already told you, electrons, just like everything in our universe, likes to move towards lower energy. So this electron that's up here in this higher energy level does not like to have all that extra energy. Right now, it's in its excited state. It wants to always be in its ground state. It wants to go back to that first energy level. So what does it have to do in order to be able to go back to the other energy level?
Release a photon.
It's got to lose the energy. A quantum of energy is the minimum energy gained or lost by an atom. It gained a quantum of energy to move up. It's got to lose that quantum of energy to come back down. So, when it does that, it can come back down to its original position, but it has to give off the same frequency of light. Yes?
So light is the energy that the electron gets off when it moves back down through its non-excited state. That's how
Yes.
you see light.
Yes. Now, this light that's given off is a very specific frequency. That corresponds to one of the bands on its atomic emission spectrum. The transition, and these are called electron transitions, the transition from energy level 1 to energy level 2 in a hydrogen atom corresponds to the red line that we see on the atomic emission spectrum. Okay?
So the light is only like appearable whenever it's brought down.
I'm sorry, one more time?
So you can only like physically see the light, like the energy, whenever it's at its down state, correct?
Correct, in its ground state, yes.
So if it goes up, then what would it be at that point?
So, hydrogen itself, we don't typically, there's hydrogen in this room. It doesn't have a color to it until we cause those electrons to transition back and forth. When we had that hydrogen lamp here, it had a reddish tint to it because this is the dominant transition that's happening. That red band is more prominent than the others, so what we see or what we perceive as a red light. But that's only when we're constantly feeding it electricity or constantly feeding it energy. So when we throw energy at this, we're throwing usually the whole electromagnetic spectrum. Remember we talked about absorption spectrum? These ones here where there's a band that's missing. So if hydrogen was in front of all this energy, what we would see are those 4 missing bands because that energy has been absorbed by the atom. Eventually, the electron is going to, we call it relax. It gives out that energy, it relaxes back down to its ground state. When it relaxes, that's when we see the bands that are being emitted. This process happens very, very fast. And it happens a lot when we're putting energy, purposefully putting energy into it, like when I had that lamp up here. If we had a camera that could videotape that and we could look at it in slow enough motion, you would see a flickering. Right? Because no light is given off when it goes up, but light is given off when it comes down. So, and it only has 1 electron, so it depends on where the electron would happen to be. And you'd also see that it would be red, then more blue, then more purple, then red, then, you would see the different transitions that were occurring. But red is the most prominent, so that's the one that's how we perceive that color. So then how do we form the blue or the purple bands? Well, the key is in the fact that there's an infinite number of energy levels. What was that?
So hydrogen doesn't only have to give off red?
No. The atomic emission spectrum has 4 bands in the visible spectrum. 1 red, 1 blue, 2 purple.
The 2 purple, is that just what appears to us, or is I genuinely visible?
There are 2 bands in the violet portion of the spectrum. And up here, this is an angstrom, so it's not as, it's about 4,200 angstroms and 44, just under 4450. It's times 10 to the negative 10. So,
That makes a lot of sense.
and then the blue one is here between 4,700 and 5,000, and then we have a red one up here about 6,550.
So scientifically, the term will not apply.
We label colors as specific colors, but we've all seen, right on the borders, we've seen those things where somebody says it's blue and somebody else says it's purple. It's just, these 2 are in the violet portion of the spectrum.
Okay.
So they would line up with, you can see this color here, and they would line up right in there,
Okay.
okay? So because there's an infinite number of these rings, that electron doesn't just have to go to energy level 2. It can go to energy level 3 or 4 or 5 or 700 or whatever. And the farther it has to jump, the more energy it requires, which means it needs higher energy frequencies.
So is that what you're talking about, like you said, like something volts?
So then that affects how we see it then, so like how much energy, so then how far it has to jump, then its way back.
And if we don't know, I don't know. We're not gonna discuss it here. This electron can jump up to energy level 3. Then when it relaxes, it can come down to energy level 2. That's a different frequency of light. And it can go from 3 to 1. That's a different frequency of light. It can go from 2 to 1. That's a different frequency of light. So the way it makes its way back down is going to affect the bands that appear on the atomic emission spectrum.
So it necessarily, like you said, so if it starts at 1, and it doesn't have to go straight back down to 1, it could have a rest.
Right.
Okay, and the same like way vice versa, if when the energy is given off, it doesn't have to go 1, 1, 1. It can go straight to the one that it has based on the energy level.
Yep. Now, somebody in the other chemistry class asked me if the amount of energy to go from 1 to 2 is the same to go from 2 to 3. And the answer is no. Every atom is unique. That's why their atomic emission spectra are unique. So the distance between those energy levels is different. And that creates that unique fingerprint that we see for the elements. So now, does any of that stuff make a little more sense? questions do you have? Or are we at the point where I don't even know what to ask? Because that's kind of where we were at in fifth period.
I understand like all of that because of all of that.
There's no flow.
Good.
Yeah, I just
Like
needed to
when-
connect to
When we were talking about this is kind of like a bunch of random stuff.
Yep. Yep. And this is such heavy material, it just takes a little time before we can wrap it all up nice and neat. Yes, Melina?
I think I need a little more explanation on the equations and what they like show. So like for the frequency, wavelength, and light, that just shows the relationship.
All equations show relationship.
Right. So just what they have. Okay, just what they. Ignore it. I got it.
Okay. I'm not really sure what you need from me, so if you decide, let me know.
Okay, I think I got it.
Okay, yes, Hayden?
Can you explain the other circles around there a little bit more?
Yeah, so, if this, in order to go farther away from the nucleus, it needs more energy. So this green wave might get it to the second energy level. In order to get it to the third energy level, we might need to have a wave, that has a higher frequency that looks like this. See how it's more bunchy? That's the technical term, bunchy. Or I just made it up. Okay, so if this is the right frequency, then that electron can absorb it. It'll absorb that energy, and that could cause it to jump to the third energy level.
So will that make it more brighter as it comes down?
No, it doesn't have anything to do with intensity, brightness or dimness. It has to do with frequency. So when this relaxes back down, if it comes back down to 1, then it could give off a higher frequency light. And that brings us back to this here. Red has the lowest frequency in the visible spectrum. So if we have that purple one that I just drew, we might get a yellow light or a green light. It's gonna have a higher frequency.
So the different frequencies give off different colors.
Yes, and that is these bands here on this spectrum.
You said red has the lowest frequency?
Melina?
Alright. I know that hydrogen only has one electron, but what happens when you go to a different like element that has multiple electrons and they're all jumping at the same time?
Like helium?
Yeah.
Okay, helium has 2 electrons.
Yeah.
His model didn't predict, it only predicted for hydrogen.
Because it
Correctly.
only has one.
Yeah, so when we have more than 1 electron, things get super crazy, because you can have all those different electrons transition from different places. And remember when I had you look at this light? Wasn't that more complex than anything you observed from that carousel?
Yeah.
Because I don't know what's in there, but it used to be mercury, and mercury has 80 electrons. So it's just like a solid spectrum. You can see some darker bands than others, but it looks solid.
It's that middle one.
Because the more electrons you have, the crazier it gets. And Bohr's model did not predict anything except for hydrogen correctly. He tried, but he just couldn't make it work. Hey,
So what's the frequency in white light?
white light is a combination of all light.
there's all
So
different frequencies?
it's a range of frequencies. That's why when you split it with a prism or a raindrop, you get the whole spectrum because it's all the frequencies there.
Oh, okay.
Okay?
Ah, that makes sense now.
Okay, so we knew, after all of this information came out, we knew that Bohr's model was a better model than Rutherford's. But it still wasn't the model. However, we use Bohr models as a teaching tool because they do a good job of tracking things for us. So I'm gonna go to the next slide.
So all this information was right though, but he only found it for the one.
Yeah, the model's not right, but he was able to show that there has to be structure to the electrons. Otherwise, he never would have been able to predict the hydrogen spectrum. Okay?
Like what we use, like when you do like the Valence show.
That's using Bohr's model. Yep. And we're gonna draw Bohr's model because, like I said, it's a very good teaching tool. And what's really important for us as chemistry students or chemists in general is to know what the electrons are doing, because all the interesting stuff that atoms do is because of their electrons. So, just a summary. Bohr's model shows energy levels of the atoms as orbits around the nucleus, and those energy levels are populated with electrons. So we put electrons in there, and we just, we have them in there in a very specific way, but those energy levels are there to hold electrons. The maximum number of electrons per ring, per energy level, per shell, starting nearest the nucleus at energy level 1 is 2, 8, 18, 32, 32, 18, 18.
What?
Yep,
Is it a pattern or just 18 goes on forever?
there's a pattern.
So does it start back up at 8? I mean 2?
Nope.
What?
These are ground state, and we can only have 7 right now.
That's the only thing we can see.
Yep. It's the only thing that can exist. Right now.
There's so much we really do not know.
I know.
Yeah.
This is so complex.
Don't worry, we're gonna uncover more of the story in the coming days.
Because I feel like when you ask us stuff, like, you're being rhetorical, like, we don't know this yet. I'm like, oh, we're gonna talk about it, but like, you literally mean we do not know it.
Yeah.
So it's like, oh.
When I'm talking about it here, I'm talking about the scientific community in the early 1900s or the late 1800s. And again, think about this. This was just over 100 years ago that this came out. Okay? So the maximum number of electrons per ring, starting with energy level 1, is 2, 8, 18, 32, 32, 18, 18. I do not have that memorized, but I can tell you if you give me a periodic table. And we're going to talk about that in the next couple of days. And then the last thing I have up here is that you can have no more than 8 electrons in the outermost ring at any time, which seems totally counterintuitive, right? Because you can have a maximum of 18 in that last energy level. I just told you that in the bullet point before it. But we're going to talk about that as well. These are conditions of Bohr's model as we use it in a teaching tool manner. But all of this is going to make a little more sense after I show you a few things, okay? But it's too much at one time. So I can only tell you a part of the story here and there and foreshadow for later, okay? So I'm gonna stop here and leave it at that.
Check your
Yay.
homework.
And check your homework and talk about your homework. Thank you. See, I'd already forgotten. So let me get my, I'm gonna go ahead and stop this.